be here.
Having a few technical issues, so we're just waiting for, and for those just joining, we are having a small technical issue, so we're just waiting for a few more people to join and we'll get started. We'll give them about another 1 minute to start, to join us. Thank you so much. Thank you everyone for your patience. I think at this point we'll get things started. So I do again want to thank everyone for joining us. Anyone having technical issues joining the session, we apologize. But thank you again for persevering and joining us today for this exciting webinar being brought to you by Scintica Instrumentation. My name is Tanya Coulthard and I will be your host for today's webinar. Our webinar today is entitled The Basics of Photoacoustics and Fluorescence Tomography. Today's webinar will be given by Dr. Parajita Verma, and Dr. Verma is an application specialist here at Scintica, having recently completed her PhD in Cancer Sciences at the University of Buffalo. Throughout her thesis work, Appy was focused on evaluating the potential applications of various imaging techniques in monitoring the response of tumors to various therapies, both preclinically as well as clinically. In her role at Scintica, Appy works with our customers to help them achieve their research goals, using the full complement of products within our imaging as well as physiology and molecular portfolios. During today's webinar, Appy will review some of the basics of photoacoustics as well as fluorescence imaging, along with some of the principles of these modalities as they relate to tomographic imaging. As some of you may know, Scintica Instrumentation is the distributor of PhotoSound's TriTom systems here in North America. Today's webinar is the first of a 4-part series, which we hope to resume in the fall as everyone returns from their summer break. Today's webinar will introduce the modality, while future webinars will introduce the specifics about the TriTom systems, with the series finishing up with a live virtual demonstration towards the end of the year. Please keep an eye out for these emails in the next few months with additional information about the upcoming webinars. Before we begin, I'd like to briefly mention a few housekeeping items. We do anticipate today's presentation will be close to 55 minutes, so we may not have time to answer any questions live. However, please feel free to submit your questions in the Q&A dialog box, and I'll work with Appy to get answers out to everyone in the form of a transcript. This transcript should be sent out over the next few days. Please also note that we are recording today's session, so if for some reason you lose the connection or can't hear anything clearly, you will have access to the video file for you to review later. So without further ado, I'd like to turn things over to Appy.
Thank you, Tanya, for the introduction, and good morning, everybody. Thank you for joining us today for the webinar. Today, I will be talking about the basics of photoacoustic and fluorescence tomography, also known as PAFT. The PAFT system is designed by PhotoSound, and we at Scintica are the distributors of this system. If you have any questions regarding the system, please feel free to reach out to us, and we will get back to you with the answers. So the PAFT system uses high sensitivity of the fluorescence imaging as well as high spatial resolution of the photoacoustic imaging. This system uses light as the main input. So in today's talk, I will be talking about the motivation and challenges in imaging, a brief background about what is photoacoustic tomography and fluorescence tomography. Then I'll go over the PAFT system. I will also cover the applications and the current research using this system, and finally the take-home. So the first point, that what is the motivation and challenges in imaging? Imaging has been an indispensable tool in preclinical and clinical research. In the past 3 decades, there has been a huge increase in the number of imaging technologies and their application. As you can see in this image, there are different technologies that have been used for imaging. The imaging systems can be grouped by the energy used to derive visual information, the spatial resolution that is attained, or the type of information that is obtained. For example, as you can see in this figure, based on the spatial resolution, for example, macroscopic, microscopic, or tomographic view, we can characterize or differentiate different imaging modalities. For microscopy, we use bright field imaging or confocal microscopy. For tomography, we have fluorescence tomography or photoacoustic tomography. And for the macroscopic reflectance, we have bioluminescence imaging or lifetime FRI. For the current talk or for today's talk, we will be focusing on the tomography, specifically fluorescence tomography and photoacoustic tomography. And both these sources, as I have already mentioned, utilizes light as the main source or input. So what is the motivation for imaging with light? The first and the foremost thing is the safety. This imaging modality uses non-invasive imaging and non-ionizing radiation. The light that is used is in the visible range and does not harm or have any ionizing effect. The second thing is the optics. Using light, we get high intrinsic contrast. There could be endogenous contrast, for example, lipid, water, hemoglobin that is found in our body can act as a source of contrast agent. And this helps us for functional imaging. For example, hemoglobin in our body, which is bound to oxygen, and the other part which is not bound to oxygen, is that can give us the information about the oxygen level within our target. For example, it can also tell us whether our region of interest is hypoxic or not. From the physics perspective, it gives us the molecular structure and composition of our target. And it also helps us to image the disease marker. As I have told you, we can image hypoxia in case of cancer, which is one of the negative prognostic marker in case of imaging. These imaging modalities can give us functional information which is analogous to the information that we get from MRI. We can also get metabolic information which is analogous to PET. We can do label-free histologic imaging of cancer without excision. And it also helps in molecular imaging of disease markers. As I have already told before, we can image different disease markers using this imaging modality. The current technologies in optical imaging is confocal microscopy, two-photon microscopy, optical coherence tomography, and many more. However, there are certain challenges of optical imaging. One of the main challenges in case of optical imaging is the depth of light penetration. Light can be scattered or diffracted before reaching the source. The signal generated depends on the illumination of light at different wavelength. And this wavelength is chosen based on the optical property of the target and the background medium. So as you can see in this image, in case of confocal microscopy, the depth of penetration is only 200 microns. In case of two-photon microscopy, the depth increases, but it only goes to 1.5 millimeter. Photoacoustic microscopy have a penetration depth of 5 millimeters. Similarly, diffuse optical tomography has a penetration depth of 1 centimeter. However, as you can see here, photoacoustic tomography has high depth penetration of up to 7 centimeters, which actually answers one of the challenges, that is poor penetration of light source. So photoacoustic tomography has one of the advantages that it has high depth penetration up to 7 centimeters to 10 centimeters. Besides lack of depth penetration, there are various challenges of optical imaging, such as approximation and misinterpretation of the data. As you can see here, this is a two-dimensional image, whereas on the rightmost, you can see the three-dimensional image of the mouse. The advantage of using the 3D tomography is that signals are reconstructed and repositioned into the three-dimensional representation of the mouse. We are able to get clear details on the signal size and localization. As apparent in this image, we can see where exactly the signal is coming from in these images. This suggests the advantage of 3D tomography over the conventional 2D optical imaging. In the next few slides, we will be going over the 3D tomography, specifically photoacoustic tomography and the fluorescence tomography. So looking at the photoacoustic tomography, the photoacoustic effect is not something new. It was discovered in the 19th century and was first reported in 1881 by Alexander Graham Bell. The concept was light in and sound out. They found that when light was focused on a selenium cell within a metal receiver, the cells produced sound. So Bell's photophone consisted of a selenium cell and an electrical telephone receiver. When light fell on these selenium cells, sound waves were generated, which could be heard by a person on the other end. So light in and sound out was the concept of the photoacoustic effect. So now moving on to the photoacoustic tomography. Photoacoustic tomography is also based on the similar concept, that is light in and sound out. When the light falls on our target, the chromophores in the tissue will absorb light. For example, hemoglobin, which is one of the chromophore, can absorb light. Now this light is then converted into heat through a non-radiative relaxation, leading to thermoelastic expansion. Post-thermoelastic expansion, pressure waves will be generated, which would then lead to acoustic signals, which can be detected by the probe. So basically, photoacoustic tomography is light in and sound out. Various imaging agents can greatly enhance the photoacoustic imaging contrast. There are typically two types of contrast agents. One is the endogenous contrast and the other one is an exogenous contrast. So photoacoustic imaging takes advantage of the fact that the body tissues contain a variety of endogenous chromophores with different absorption spectra. As you can see in this image, there are various endogenous chromophores such as melanin, water, oxy and deoxyhemoglobin, and many diseases causes changes in the tissue composition, which can then be visualized using photoacoustic imaging. For example, just to look at the level of oxygen, we can look at oxygen that is bound to hemoglobin and that which is not bound. So unbound oxygen and bound oxygen can be measured using photoacoustic tomography. The other type of contrast agent is the exogenous contrast agent. These could be non-targeted or targeted contrast agents. The advantage of using targeted imaging agent is that they can provide specific information on molecular or cellular processes in the tissue. There is a great variety of imaging agents that can be used for photoacoustic imaging. As you can see here, there are different agents such as methylene blue, nanomaterials such as gold nanorods or nanodroplets, or single-walled carbon nanotube. The imaging dyes that have been approved for human use is Evans blue, methylene blue, and ICG or indocyanine green. The rest of the imaging agents are not yet approved for imaging in humans. But overall, the contrast agents that can be used could be the endogenous contrast or exogenous, and within exogenous, these contrast agents could be targeted or non-targeted. As we have already seen in our previous slides, the spatial resolution of photoacoustic tomography is significantly high, as well as the depth penetration is high in case of photoacoustic tomography. The images here on the right, we can see the images from the microscopic level of the organelles to the whole body, small animals, or in case of humans. When we compare photoacoustic imaging with other modalities, we found that photoacoustic is a high-performing imaging system compared to other modalities. Photoacoustic is often referred to as optoacoustic, so you will see optoacoustic a lot of times. In this figure, the dot colors indicate relative performance in clinical and preclinical setting. The green here is excellent performance, yellow is average performance, and red is poor performance. As you can see in this figure, optoacoustic has a lot of excellent performance in different sections. It has excellent depth penetration, excellent contrast, better specificity. It also gives information at morphological, functional, and molecular level. It uses non-ionizing radiation and is associated with low risk and side effects. The scanning time is significantly low and it is easy to use. One of the best advantages of optoacoustic or photoacoustic imaging is the patient convenience. Because of its ease of use, it is very easy to image patients using photoacoustic tomography. Compared to other imaging modalities, as you can see, optoacoustic or photoacoustic imaging is the best or high performing imaging system. So one of the optical chromophore is hemoglobin, which is found in our body. This hemoglobin can be bound to oxygen or it could be free. So oxyhemoglobin, which is blue in color and blue in this graph, is bound to oxygen, and deoxyhemoglobin, that is unbound oxygen to hemoglobin. So in case of deoxyhemoglobin, the absorption coefficient or the wavelength is 750 nanometers, whereas for oxyhemoglobin, the absorption coefficient, maximum absorption coefficient is at 850 nanometers. When we take the ratio of oxygenated hemoglobin to deoxygenated hemoglobin, we can get the value of oxygen saturation. We can also figure out total hemoglobin in our tissue by looking at oxygenated hemoglobin plus deoxygenated hemoglobin. And this is widely used in cancer research, where we can look at the oxygen level within the tumor or around the tumor. We can also look whether these tumors are hypoxic and can predict the response of the tumors to various therapies, where hypoxia will be one of the negative prognostic marker. So the advantage of photoacoustic tomography is deep tissue imaging. We know that it has better depth penetration and better spatial resolution. It is ideal for 3D imaging because it has 300 micron resolution, and it also gives anatomical reference. For example, skin and vasculature can be used as the reference sites. Photoacoustic tomography has a wide range of clinical applications. It can be used in case of brain imaging, to gastrointestinal tract or endoscopy. In looking at the atherosclerotic plaques in case of cardiovascular system, it is also used in various cancer, for example, ovarian, head and neck or breast cancer. It can also be used to study arthritis in bone cancer, thyroid imaging and eye disease. The image here is obtained from a photoacoustic tomography machine where researchers use to image brain activation. This image is the resting state, and they also look what happens when the brain is active. You can also look at hallmarks of cancer. In this case, they are looking at the hallmark for melanoma cancer. So photoacoustic tomography has a wide range of clinical applications. Because of its wide range, the number of papers or total number of presentations in conferences as well as the articles that are being published has increased significantly over the years. There is a huge interest in photoacoustic tomography, and a lot of articles and presentations are just focused on photoacoustic tomography in preclinical as well as in clinical space. So now, as we're aware about the basics of photoacoustic tomography, which in short is light in and sound out, we will next look at fluorescence tomography. So fluorescence tomography is a three-dimensional, optical, non-invasive imaging modality. The image on your right is one of the images that was captured using fluorescence tomography. This imaging modality allows to determine the position and the quality of a fluorescent source in vivo. It also gives the ability to detect deeper fluorescent source and can be used to gain functional as well as biological information. In case of fluorescence tomography, fluorescence occurs at low energies or longer wavelength. When light falls on any object, the electrons get excited to a higher energy level. Once in the higher energy level, the electrons try to come back to the ground state level, and in this process they emit fluorescent light. There are different fluorophores which needs to be excited at the particular wavelength in order to emit fluorescent light. There are three simple steps of fluorescence imaging. The first one is excitation of an injected fluorophore. Once the fluorophore is excited, emission of fluorescence light upon spontaneous emission of a photon will take place. And this emission of the fluorescent light can then be detected using a CCD camera using appropriate filters. There are different tags that can be used for fluorescent imaging. These tags can be targeted. They could also be targeted to vasculature or labeled, and these tags can be activatable. Based on what the tags are being used for, fluorescent imaging has shown to be used in a wide variety of disease area. For example, it is used to image arthritis, bone remodeling, cardiology, infectious disease inflammations, as well as in the space of oncology and pulmonary diseases. So now we know that photoacoustic imaging and fluorescent imaging are both used widely in the preclinical as well as in the clinical space. The PAFT system combines both of these modalities together, and in the next few sections, we will be going over the applications and the current research using the PAFT system. The photoacoustic and fluorescence tomography is an innovative and a compact system. As you can see here in this image, this is how the machine looks like. It simultaneously co-registers orthogonal photoacoustic and optical projection. It utilizes high spatial resolution from photoacoustic imaging and superior molecular sensitivity from fluorescence tomography, all of this on one platform. So this is a machine which is very compact, and this PAFT system consists of four main modules. The first one is the imaging module, which is here. The second one is the data acquisition and the control module. The third module is the water module, and the fourth module is a desktop computer which is attached to this system. The data acquisition and the control module, which is on the right hand side, houses the control electronics, power supplies, data acquisition circuit boards for the PAFT system. The control panel located in the front of the system which is here, displays temperature monitoring information and has analog user controls. The water module here circulates conditioned, filtered and degassed deionized water around the mouse to facilitate the photoacoustic imaging. The water filtering and circulation components are located below the imaging module. And this part here is the imaging module. We will be discussing more about it in the next slide. Moving on to the imaging module, this is the schematic overview of the PAFT system. As you can see here, it has 6 different parts. The first part is the ultrasound detection array, which detects the ultrasound that is generated. The second part is the animal holder, where the animal is placed with a nose cone, and this nose cone is attached to the isoflurane chamber. Third is the water tank, and as I have mentioned, the imaging module is on top of the water module, and the water module maintains the temperature of the water tank. The temperature of the water is always maintained at 37 degrees Celsius. Number 4 here is the heating pad, which makes sure that the temperature within the system is maintained. One of the best features of the PAFT system that differentiates it from the existing imaging modalities is that it has 2 tuning range, one in the range of 690 to 950 nanometers and the other one in the range of 1200 to 2400 nanometers. The PAFT system uses 2 optical fiber terminals, which is number 5 and number 6. One of the fiber terminal is called the orthogonal excitation terminal, which were mounted in the imaging chamber orthogonally to illuminate the object of interest. The other one or the other fiber terminal is the epi excitation terminal, which is placed 30 degrees with respect to vertical plane of the transducer and is used to deliver light at 532 nanometers. So there are 2 terminals. One is the orthogonal excitation terminal and the second one is the epi excitation terminal. The system has a field of view of 30 into 30 into 30 millimeters with a spatial resolution of 150 micron provided by the PhotoSound manufacturers. Moving on to the PAFT workflow. On your left, you can see the PAFT workflow. So once the animal is imaged, cross-sectional or 2-dimensional images are captured. These 2-dimensional images are then constructed to form a 3-dimensional or tomographic image. The optoacoustic or photoacoustic images are tomographically reconstructed using different values of the speed of the sound. Thereafter, these reconstructed images are processed using the autofocusing algorithm, and the focus measures are employed to determine the best matching speed of sound. Based on this algorithm and the computed speed of sound, the 3-dimensional image is reconstructed. This is an example of a 3-dimensional image using the PAFT system. This is actually the placenta within the abdomen of a pregnant mouse, and there are different regions which are being depicted in this image 3-dimensionally. Next, I'll talk about the laser settings. So the laser setting dialogues allows the user to control the laser. So the wavelength of light is one of the important factors in case of PAFT system. To image the target or of interest, we need to modulate the wavelength. So the users can choose the output wavelength by either typing the wavelength in the wavelength text box, or they can use the switch. The switch allows the user to select 532 nanometers by default, but in case they want to use a variable wavelength, they can turn off the switch and switch on the wavelength. The filter info will display the current filter position of the filter wheel. So the laser will not fire if the chosen wavelength will pass through the active filter. And the default value is 650 nanometers for the wavelength. The second part of the laser setting is the laser power. So the value that changes the laser power output is the active laser output. And a value of 100 will have maximum energy output, and a value of 0 will have no output. The laser power number is based on lengthening to shortening the Q switch delay. And the laser power use external power meter. There is an on-off switch on the laser power, and this on-off switch will activate or deactivate the laser externally. So if the status bulb is yellow, the laser is active, and if the status bulb is red, the laser has an error. The default laser power here is 0. So the third component is the laser power. And the fourth component is the filter wheel. The filter wheel is a variable knob that selects the filter wheel position to set as active. So the service switch is disabled in this case in our filter wheel, and the status bulb is blue when the filter is idle or set, yellow when the filter is busy, and red when the filter wheel has an error. So laser settings, which is one of the important factors in the PAFT system, has three parts, that is laser wavelength, laser power, and laser wheel. So as I had already talked, PAFT is light in and sound out, and the camera setting helps to capture the images. We have already seen the light in or the laser setting, and now we will look at the camera setting, that is the sound out. So the camera setting dialog allows the user to customize the optical imaging modality setting. There are different buttons. The first one is wait for trigger, and if this is checked, the camera will save the frame rate or the frame data at each trigger event. Then the second is the limited capture frames, and when this is checked, the camera will only capture the specified amount of frame data in the number of frames per scan events. The resolution allows the user to select the resolution to save the frame data. So you can change the resolution as per your convenience, and by default the resolution is set to 2048 into 2044, or the resolution is set into 1024. So based on the resolution that we want, we can select the resolution. Number of frames that are captured. If limit captured frames is enabled, the default value is 1000. So number of frames that are captured by default will be 1000, and the range here varies from 0 to 1 million. So that is the total number of frames that can be captured. Then apart from that, the other thing is the exposure time. So exposure time sets the exposure, as the name suggests, it sets the exposure time of the camera, and the default value of the exposure time is 10 microseconds. Then we have the right level and the left level, and the right level sets the ceiling of the camera's dynamic range to the default value of 65535, and the left level sets the floor of the camera's dynamic range to a default value of 0. The gamma correction value of the camera is set to 100. Then we have the region of interest, which allows the user to select the region of interest to capture. So this gives the user a freedom to select whatever their region of interest is, and the default value of the region of interest has a resolution of 1024. The width and the height can vary, which could be 2048 or 1024, and based on that, the image will be captured. The gain settings are set to normal, which is low gain, high gain, and HDR. And the default for the gain setting is normal. We can always change it to high or high definition gain settings. But it should be kept in mind that once the gain setting has been set during a study, the gain setting should be maintained throughout the study for each individual studies. So it could change between the studies, but it shouldn't change within the study. So that is the camera setting. The 3D reconstructed volumes of the PAFT data is shown here. So as you can see here, the mouse is held on the stage, which is connected to a nose cone, and that nose cone is then connected to an isoflurane chamber. Gas bubbles are created, which helps in the normal breathing of the mouse. And then there is this ultrasound detector. The image that is generated using the PAFT system can give the spatial localization of various organs within the mouse. For example, in this image, as you can clearly see, this part is the spleen. You can see the liver, kidney, ovarian vessels, and inferior vena cava. The advantage of the PAFT system is that it has high spatial resolution and high sensitivity. Moving on to some of the applications of the PAFT system. So the phantom experiment or an in vitro experiment was performed to determine the system's sensitivity by measuring the acquired signal of ICG. And ICG, as I had already mentioned, is isocyanide, which is commonly used to generate photoacoustic imaging contrast. So as you can see here, this is a cross-sectional view of the phantom, which is filled with ICG at different concentration, ranging of OD of 0 to OD of 1. So different concentrations of ICG is filled in the phantom. Then this phantom was imaged using PAFT, and the image was reconstructed with the slice in the Z direction of 150. The brightest signal is from the OD of 1, and there was no signal where the OD was 0. The variation of signal intensity with optical density was plotted. As you can see here, the y-axis is the photoacoustic signal intensity and the x-axis is the optical density. As the optical density increased, the photoacoustic signal intensity also increased. Therefore, there was a linear relationship between the photoacoustic signal and the optical density. This data suggests that there was high sensitivity of the PAFT in phantoms or in the in vitro setting. Because the in vitro setting is based on homogeneous concentration of ICG, it was important to see whether PAFT can image different regions of interest in vivo. So in vivo 3D PAFT imaging of mice is shown in this figure, where figure here A is the image of the lower abdomen, P is the placenta, and C is the carotid artery. Figure B is the skin vasculature, and when this figure A and B was superimposed, we were able to see both the placenta, carotid artery, and the vasculature. PAFT was also able to image the spine within the aorta, the spiral arteries within the placenta, and the uterine vasculature of a pregnant mouse. So overall, this image suggests that PAFT was able to image pregnant mice over a period of time. One of the advantages of the PAFT system is that the contrast agent can be endogenous or exogenous, and it is also used to study disease markers. So one of the study tested the ability of the system to detect changes in hemoglobin that was bound to oxygen and the unbound hemoglobin concentration in the placental tissue in vivo. They performed oxygen challenge experiment by varying the ratio of oxygen in the anesthesia carrier gas. They created a normoxic condition. They used 3 different wavelengths to image, that was at 690, 808 and 950 nanometers. And they were able to look at the concentration of hemoglobin that was bound to oxygen and the unbound oxygen. Based on that, they were able to calculate the SpO2, that is the oxygen level within the tissue. So as you can see here, this is the placenta and CA is the carotid artery. So the researchers looked at the level of oxygenation in the carotid artery as well as in the placenta. Figure B and figure C are the relative SpO2 or oxygen saturation. The top panel here is the oxygen saturation in the placenta and the bottom here is the oxygen saturation inside the carotid artery. The readings here show that the SpO2 in the placenta did not change as the oxygen or the arterial oxygenation was changing. However, in case of carotid artery, as oxygen was changing, PAFT system was able to detect the changes in the oxygen level, and there was an increase in the SpO2 as the oxygen increased. This was a 3-dimensional image where the red here is the highest oxygen saturation and the blue is the lowest oxygen saturation. Based on this calculation, the SpO2 levels were detected. And the data here is consistent with other published literature using different modalities, which shows that within a pregnant mouse, the placental oxygen does not change. However, it is the carotid artery which shows a change in the SpO2 level. Therefore, PAFT system was able to image the hemoglobin oxygenation at 100% oxygen supply. After looking at the endogenous contrast, it was important to see whether the PAFT system can image exogenous contrast. So exogenous contrast, which is folate bound to ICG, which was pegylated, was used as a contrast agent. So this here, the image here is a baseline image of the placental tissue. The image after that is the image captured after 5 minutes of injection of our contrast agent. And the third image is the concentration after 90 minutes of injection of the contrast agent. The green here, this is a pseudo-polarized map where the highest is green and the lowest is black. So as you can see from this image, at baseline there was no contrast, and post-injection there was an increase, and at 90 minutes there was a significantly higher levels of folate-bound ICG. When they plotted it, they were able to see that with time the photoacoustic signal intensity increased, and this was directly proportional to the amount of folate that was found in the placenta. So just to give you an overview of how these images look. So this is the image at 0 minute when the contrast was not injected, and as you can see there was no signal. At 5 minutes when the contrast was injected, there was an increase in the signal, but it wasn't significantly high enough. But after 90 minutes, using photoacoustic imaging, we were visually able to see that there was a significant increase in the folate uptake. So this modality helped in the longitudinal monitoring of an exogenous contrast in the placental tissue, highlighting one of the advantages of the PAFT system. The applications of the PAFT system could be seen in the cancer setting, where we can look at disease markers in cancer. PAFT can also be used in neuroscience. As you can see, this is the image of a resting brain, and PAFT can be used to image brain. PAFT can also be used to look at the metabolism. This image here shows the glucose uptake within a mouse. So PAFT was able to look at the metabolism. I have already shown you that PAFT can be used to image the placental oxygen during pregnancy. Besides that, the application includes reporter gene expression. It can also be used in cardiovascular setting and to study tissue regeneration. So there is a wide range of applications that PAFT can be used in. And in all these applications, the advantage of using PAFT is to get a better spatial resolution as well as a deeper or higher sensitivity. The advantage of using the PAFT system is the deep tissue imaging. The photoacoustic tomography provides deep tissue imaging as it enhances the depth penetration and increases spatial resolution. It is one of the ideal three-dimensional imaging modalities, and as we have already seen, it can give us anatomical references because we are able to image the skin, we are able to image the organs, so it gives a clear anatomical reference where the blood vasculature and skin can be the site of reference. Using the fluorescent tomography along with photoacoustic tomography leads to the reduction in background noise. And as we are using fluorescent microscopy, it also increases the sensitivity of this imaging system. Therefore, this imaging system perfectly co-registers the imaging modality, which brings together photoacoustic imaging, and the advantage of it, as I have already highlighted, is spatial resolution, and fluorescent imaging, which increases the sensitivity of the image. So now we have already gone over the basics of photoacoustic tomography and fluorescent tomography. I have shown you the applications and the current research of PAFT. So the take home is that this multimodal PAFT technology enables the simultaneous acquisition of the signals from photoacoustic, fluorescent, as well as bioluminescent source at each rotational position of a studied living sample. So this imaging modality is actually, it brings in vivo molecular imaging to the level of highest fidelity, enabling quantitative volumetric measurements and up to 10 times improvement in the spatial resolution in comparison to the state-of-art optical methods. So as I have already shown, the spatial resolution is one of the important factors, and the PAFT technology enables quantitative volumetric measurement and up to 10 times improved spatial resolution, which is one of the big breakthrough in the field of preclinical research. Three-dimensional visualization of optically labeled biological structures are also possible, and the resolution is around 100 to 150 microns. So this instrument benefits from the exceptional molecular sensitivity, which is from the fluorescence tomography, and the photoacoustic tomography enables functional imaging with high spatial resolution. This actually helps this PAFT system is used for 3D localization of anatomical, functional, and molecular data. And one of the advantage of the PAFT technology is that it provides in vivo tracking, mapping, and longitudinal studies of externally labeled as well as internally expressed, that is exogenous as well as endogenous light emitting or absorbing molecular constructs. So these are some of the advantages of the PAFT system. Stay tuned for our next webinar where we'll be talking about the TriTom PhotoSound system in more details and about the machine in general. Thank you for your interest. And if you have any questions, you can always email us and we will get back to you with the answers. Thank you.
Wonderful. Thanks, Appy, so much for that great presentation. At this point, I would like to launch our audience poll. So bear with me as I get that launched. This poll is just to gather a bit more information about your experience with either fluorescence or photoacoustic imaging, and if you're doing that in a tomographic form at this point. And then also we're interested in getting a little bit more information if you're using other imaging modalities in your work. So here at Scintica Instrumentation, we have a whole line of imaging products, and we're just curious if you are also using those in the work that you're doing at your different institutions. So we'll give everyone just a few minutes, a few moments, sorry, to reply to those. And again, thank you for your attention during today's webinar. A reminder to those who have questions, feel free to use the Q&A dialog box to enter any questions that you do have. And as much as I can, we'll answer a few of those just before we end off today. And then any that we don't answer, I will work with Appy to get answers together to in the near future. Excellent. Thanks everyone for taking the opportunity to answer those poll questions for us. At this point, we will advance to the Q&A session. We've seen a few questions come through. I'll do my best to jump in and answer some of them on Appy's behalf. She had to run to another meeting, and so I'm just going to work through some of the questions that came in. Again, feel free to keep asking them in the Q&A dialog box. One of the questions is, what is the maximum field of view? And so for the TriTom system, again, we're going to have the 3 additional webinars in the series coming forward starting in the fall, I believe. We'll look at the dates in a few weeks' time. But for the TriTom system, the field of view is 3 centimeters in height. And then obviously we're taking that and rotate it around the animal to generate a 3-dimensional tomographic image of the animal. Should you need a larger field of view, you would simply just shift the animal's position and acquire those images and then co-register them within your image analysis software. Another question regarding how the animal is held, and a number of questions around how the animal is held and positioned within that water tank. So there is an apparatus which basically allows the animal's paws to be held. You would position the animal such that the nose was within the nose cone to allow the anesthesia to be delivered, and the animal is then submersed into that water tank that Appy was showing you. With the delivery of the isoflurane, there is a gas bubble or an air bubble, which is created to help protect the animal. And obviously the positioning of the animal is such that their nose would not be submerged underwater and throughout the imaging session. The volume of the water tank, I do have to look into what size that is, but the water is degassed before it would go into that tank. So there wouldn't be any air bubbles affecting the image quality. The water would be changed periodically. It doesn't need to be changed between every animal, but you would want to change it should there be any defecation into the water causing a cloudiness to interfere with the light or sound movement through the medium. The animals do have to have the hair removed over the area that you want to image because it is light in and sound out. So you do want to remove any interference that would be in place because of the hair as well. In terms of fluorescent channels, there's a wide variety of options just based on the laser that would be included with the system. And we'll get into more details of those options and the different models that are available in subsequent webinars, but really ranging anywhere from 330 nanometers all the way to 1300 nanometers. It, again, would be configured based on the needs and the different agents that you were looking at using, both for photoacoustics and fluorescence imaging as well. Just scanning through some other questions. We have another minute or two. The specifications for the laser source, it's going to be much simpler for me to put that into the transcript for everyone. So we will pull that together and send it out to everyone over the next few days. And I think the only other question is, what is the temporal resolution of the system compared to other imaging modalities? So again, something that we can answer in a little bit more detail in the transcript that we'll pull together, but images can be acquired quite quickly with the system and then reconstructed. Frame rates anywhere from 10 to 20 hertz, again, depending on the model of the system. So again, something we'll answer in a little bit more detail in the transcript. I'll try to provide you with some examples in different settings that would be used to get you a specific temporal resolution as an example. So again, any other questions, feel free to use the Q&A dialog box and we will answer them. We'll probably not get to them right now, but we will again create a transcript and send it out to everyone and have it available on the registration page. So at this point, on behalf of myself and API, I do want to thank everyone for taking the time to join us today for this really educational webinar on photoacoustics and fluorescence imaging and a brief introduction to the TriTom system itself. I do trust that we've been able to provide you with some relevant information and perhaps education on those modalities and perhaps a bit more as how it would relate to your studies in your research labs. As I did mention at the beginning, today is the first of a 4-part series, and we will look to restart the series as we move into the fall, ending off with a live demo of the instrument at the end of the year. So just keep an eye out for the emails towards the end of the summer, letting you know the dates of those webinars, sorry. And of course, if in the days and weeks to come, you have further questions about the instrument or the modality, please feel free to reach out to us here at Scintica and we'll be happy to discuss further. As always, I would welcome any opportunity to talk about your specific research goals and how any of our imaging systems, including the TriTom system, can help move that work forward. And thank you again for your time and your attention today. And we look forward to seeing you at another Scintica instrumentation event. Thanks so much and take care.